Equilibrium ase ꯑꯩꯈꯣꯏꯅ ꯃꯃꯥꯡꯒꯤ ꯀ꯭ꯂꯥꯁꯇ ꯇꯝꯈ꯭ꯔꯦ ꯑꯗꯣ equilibrium ꯑꯗꯨ ꯈꯪꯅꯅꯕ ꯑꯩ ꯄꯤꯛꯆꯔꯥꯏꯖꯦꯁꯟ ꯇꯧꯔꯒ ꯑꯃꯨꯛꯀ ꯍꯦꯟꯅ ꯈꯪꯅꯅꯕ ꯂꯥꯏꯅꯅꯕ ꯍꯥꯏꯒꯦ ꯌꯦꯡꯉꯨ ꯁꯤ ꯄꯤꯛꯆꯔꯁꯦ ꯎꯔꯦꯗꯅ ꯃꯁꯤꯗ ꯅꯨꯄꯥ ꯑꯃꯅ ꯑꯂꯨ ꯁꯦꯌꯔ ꯐ꯭ꯂꯥ ꯇꯧꯔꯒ ꯕꯦꯂꯦꯟꯁ ꯇꯧꯔꯒ ꯑꯂꯨꯁꯦ ꯌꯣꯟꯕꯒꯤ ꯑꯣꯜꯂꯤ ꯑꯂꯨꯒꯤ ꯋꯦꯠꯁꯤꯒ ꯑꯩꯈꯣꯏꯒꯤ ꯃꯦꯖꯔꯃꯦꯟ ꯇꯧꯅꯅꯕ ꯊꯝꯃꯤꯕ ꯁ꯭ꯇꯦꯟꯗꯔꯗ ꯋꯦꯠ ꯁꯤꯒ ꯑꯅꯤꯁꯤ ꯃꯥꯟꯅꯩꯌꯦꯕ ꯅꯥꯀꯟ ꯑꯅꯤꯁꯦ ꯃꯥꯟꯅꯔꯤꯁꯦ ꯃꯁꯤ इक्विलिब्रियमꯗ ꯂꯩꯔꯕꯅꯤ ꯑꯁꯨꯝꯅ ꯊꯣꯡ ꯃꯥꯟꯅꯕꯁꯨ ꯑꯩꯈꯣꯏꯅ इक्विलिब्रियम ꯀꯧꯋꯦꯕ ꯃꯊꯪꯒꯤ ꯄꯤꯛꯆꯔꯁꯤꯗꯅ ꯁꯃꯨꯁꯤꯅ ꯕꯣꯜꯒꯤ ꯃꯊꯛꯇ ꯂꯦꯞꯄꯤ ꯁꯃꯨꯁꯦ ꯇꯨꯗꯦ ꯕꯦꯂꯦꯟꯁ ꯆꯥꯅ ꯂꯦꯞꯄꯤ ꯃꯁꯤ ꯁꯃꯨꯁꯦ ꯕꯦꯂꯦꯟꯁ ꯆꯥꯅ ꯃꯦꯟꯇꯦꯟ ꯇꯧꯅ ꯂꯩꯕꯁꯤ ꯃꯁꯤ इक्विलिब्रियम ꯑꯣꯏꯅ ꯂꯩꯔꯕꯅꯦꯕ ꯃꯊꯪꯒꯤꯁꯤꯁꯨ ꯅꯨꯡ ꯑꯃꯒꯤ ꯃꯊꯛꯇ ꯑꯇꯣꯞꯄ ꯅꯨꯡ ꯃꯌꯥꯝ ꯑꯃ ꯂꯣꯡꯈꯠꯅꯗꯅ ꯂꯦꯞꯄꯤꯁꯤ इक्विलिब्रियम ꯃꯦꯟꯇꯦꯟ ꯇꯧ ꯂꯩꯔꯕꯅꯤ ꯍꯣꯏ ꯂꯥꯁꯀꯤ ꯄꯤꯛꯆꯔꯁꯤ ꯌꯦꯡꯉꯣ ꯑꯉꯥꯡ ꯑꯅꯤ ꯃꯈꯣꯏ ꯁꯥꯟꯅꯕꯒꯤ ꯄꯤꯛꯆꯔꯅꯤ ꯃꯌꯥꯏꯒꯤ ꯁꯦꯟꯇꯔ ꯑꯣꯐ ꯕꯦꯂꯦꯟꯁꯁꯤꯗꯒꯤ ꯂꯦꯐꯇ 10 ꯐꯤꯠ ꯔꯥꯏꯠꯇ 10 ꯐꯤꯠ ꯆꯠꯊꯣꯛꯑꯒ 50 पाउंड 50 पाउंड ꯆꯞ ꯃꯥꯟꯅꯅ ꯂꯨꯝꯕ ꯑꯉꯥꯡ ꯑꯅꯤ ꯃꯁꯤ ꯇꯣꯡꯗꯨꯅ ꯂꯩꯔꯦ ꯃꯁꯤꯗ ꯆꯞ ꯃꯥꯟꯅꯅ 10 ꯐꯤꯠ ꯁꯦꯟꯇꯔꯗꯒꯤ ꯂꯥꯞꯊꯣꯛꯑꯒ ꯆꯞ ꯃꯥꯟꯅꯕ ꯋꯦꯠ 50 पाउंड साइड ꯑꯅꯤꯃꯛꯇ ꯂꯩꯔꯕꯅꯤꯅ ꯑꯉꯥꯡ ꯑꯁꯤ ꯕꯦꯂꯦꯟꯁ ꯆꯥꯅ ꯂꯩꯔꯦ aduna nakal amatanasu hena lumde masmaina balance tong leiba thong manana leiba chang manana leiba masibu aikoina equilibrium kawe ado mathangi parada mungengo container ama leirena lorasi container du da water tap sijenerga ising khara thajalle amuksu container du dagi water tap sijenerga ising khara amuk lokthue हाइबदी कंटेनर दुदा वाटर करा इन तौरे अदुगा हाइरिबा इन तौरिबा वाटर अमाउंट तुमक अदुगी रेट तुमक यामना आउट तौरे अदु इतारगदी वाटर के बैलेंस से हेंसु हेंगलारोय तासु ताथारोय मसी वाटर की लेवल से इक्विलिब्रियम द लेबगी एग्जांपल अमनी करिगिनो हाइबा मतमदा अदुम याय with the passage of time matamna change तबगी मतुंगिना टेंपरेचर प्रेशर कंसंट्रेशन न चिंगबा सिस्टम अमगी चेंज तौद तारगदी मधु इक्विलिब्रियम का वे हाइबनी मसिदा दुम अप्लाई तौबा याय वाटर की बैलेंस से मतमना पास तौबगी मतुंगिना वाटर की बैलेंस से इंक्रीज तौदे लेंगदना लई कांस्टेंट ओइन लई अदु तारगदी वाटर की मथक्ता लेरिबा अखोगे एयर की प्रेशर से चेंज तौदेबा को अदुदना मसे इक्विलिब्रियम द लेरबनी न खनबा यायबा जानतारे को अदो हेन कुप्थाना अमुक खन्ननबा येंगो से मथंगी सिदा बिकर अनि लौरे अहान बगी पिक्चर सिदा बिकर सिदा वाटर खरा यावरे हापे बिकर से मकुम हांगदोकपा पात्रनी अहान बगी से मसी ओपन सिस्टम कवी मकुम हांगदोकपनी ना हाइदना थर्मोडायनामिक त थमग्रे ओपन सिस्टम ददी बिकर मंग द यावरिबा इसिंग दो इवापोरेशन चांग हेना थोकनी कंडेंसेशन की चांग दी यामना वाटकनी अदुना इवापोरेशन की चांग सुम हेना थोकपनी ना बिकरमंग द यावरिबा इसिंग दो कंगकनी तमना तमना अदुना मसी इक्विलिब्रियम द लेबा ngमोय कईगिनो हाइबा मतमदा रेट ऑफ इवापोरेशन का रेट ऑफ कंडेंसेशन का ओपन सिस्टम ददी मानदे अदु मथंगी लास्ट की पिक्चर नेक्स्ट की पिक्चर जी यंगो बिकरम लेरे बिकर सी की मनुंगदा इसिंग गरा हापे अदुगा बिकर से मखुम खुमजले असुमना मकुम खुमजलब सिस्टम से क्लोज सिस्टम को हाइदना थर्मोडायनामिक त तमख्रे हुजिक मनुंगदा इसिंग हापबरिना बिकर सिगी मनुंगदा लेमहौरिबा सरुक खरा इसिंग दुगी मथक थंगबा सरफेस ता लेमहौरिबा बिकर गी सरुक खरा दुदा इवापोरेशन थोकनी अहान बदai इवापोरेशन की चांग यामना वांगमगनी जरा जरा थोकनी अदुगा इवापोरेशन की चांग सुम नेमधरकनी इसिंग दुगी मथक त लेरिबा अहांग सरुकसिंग अदुदा इसिंग मनिंगी चांग सुम हेंगलकपना मरम ओइदना इवापोरेशन थोकपना मरम ओइदना इसिंग मनिंगी चांग सुम हेंगलकपना मरम ओइदना कंडेंसेशन थोलकनी कंडेंसेशन थोगा वाटर वेपर ओइना वाटर दुगी सरफेस दुगी मथक्ता लेरिबा अहांग मफम दुदा वाटर वेपर ओइना वाटर वेपर मॉलिक्यूल मयाम लाक्सल लैसलकनी वाटर वेपर मॉलिक्यूल सिंग अदु tamna amuk phandare tuna condensation process tawduna liquid water amuk olakani asumna rate of evaporation ga rate of condensation ga manarakpa tanja sang manarakpa rate manarakpa speed manarakpa tanja ama khang lakani evaporation tawriba sang duga condensation tawriba sang duga manarakpa tanja am khang lakani madugi tanja du boy koina equilibrium kaweb aduna equilibrium hariba posak ase close condition da close system da thokadabane open system da di thokte yare ko aduna evaporation buna arrow se up toroga represent tore masigi picture sida adu condensation buna down arrow na represent tore aduna nakoi equilibrium karino equilibrium si karamba condition da thoi haibasi khange ko The following topics will be discussed in today's class. They are types of chemical equilibrium and equilibrium constant. In this section, we will discuss definition of equilibrium constant and derivation of its mathematical expression using law of mass action. Okay? Aduna ngasi classes da ikone tamgadori ba topic sing adude chemical equilibrium gi makhal sing amasung equilibrium constant ni. Equilibrium constant sida ikhoina tamgadori base equilibrium constant ki definition amasung equilibrium constant ki mathematical expression law of mass action sijinaraga derivation tawba haibasi ngasigi class asida tamgani adude aikhoi matam manghandana ngasigi class asi haunaba tarasi. So without wasting any time, let's begin the class. Types of chemical equilibrium depending upon the phases, that is physical states of the reactants and products. There are two types of chemical equilibrium. They are homogeneous equilibrium and heterogeneous equilibrium. Haibagi athade chemical equilibrium gi makhal sing se kaya thona khaidokpa yabage haiba matamda reaction amada saru yariba reactant sing amasung putholagliba product sing adugi phase haibadi makhoi physical states tadip base tawrakanta chemical equilibrium haibase makhal ani thona khaidokpa yai makhoi sing adudi homogeneous equilibrium haiba mane heterogeneous equilibrium haiba amaga.
Homogeneous equilibrium, when all the reactants and the products are present in the same phase, that is liquid or gaseous phase. In a reaction at equilibrium, it is called a homogeneous equilibrium. For example, 1 mole of nitrogen gas can combine with 3 mole of hydrogen gas and produce 2 mole of ammonia gas. Okay, this 2 mole of ammonia gas can again be degraded into 1 mole of nitrogen gas and 3 mole of hydrogen gas. So the given reaction is a reversible reaction and it maintains equilibrium. And in this reaction, the reactants are in the gaseous phase and the product is also in the gas phase. That means the reactants and product are in the same phase. That means in the same physical state. So this type of equilibrium is called the homogeneous equilibrium. Haibagi after the homogeneous equilibrium karino hai taragadi reaction amana equilibrium state ta laiba matamda reaction do thokpada saruk yariba reactant sing amasung product sing na same phase sabdi same physical state ta lairaba. For example, khudam oina harabda liquid state ta ngakta lairaba natra gas state ta ngakta lairaba adu itaragadi adu gomba equilibrium du homogeneous equilibrium ka wi haigani. Khudam oina harabda nitrogen 1 mole gas na hydrogen 3 mole gas ka punja laga ammonia 2 mole gas puthokpa ngami amuksu ammonia 2 mole gas tuna kaitharak laga nitrogen 1 mole gas amasung hydrogen 3 mole gas ithokpa ngami. Aduna hariba reaction ase reversible reaction ni amasung masida equilibrium maintain tawduna lay. Asigumba equilibrium maintain tawduna layba reaction asi karama makhalgi equilibrium no hai taragade reactant nitrogen hydrogen si gas oire amade product ammonia si su gas oire aduna reactant amasung product si gi phase physical state si sab manabana maram oidana masigumba equilibrium si bu ikone homogeneous equilibrium da laire haina haigani. Heterogeneous equilibrium. When the reactants and the products are present in two or more than two phases in a reaction at equilibrium, it is called a heterogeneous equilibrium. That means, if a reaction is at equilibrium state and in that equilibrium state, if the reactants and the products are present in two or more than two phases, then that type of equilibrium is called heterogeneous equilibrium. For example, calcium carbonate, it is a solid material, okay? Calcium carbonate upon heating can be degraded into calcium oxide in solid state and carbon dioxide in gaseous state. Again, this calcium oxide and carbon dioxide can be recombined and form to calcium carbonate, which is in the solid state. So this reaction is a reversible reaction, and as it is a reversible reaction, it can maintain equilibrium. Am I right? Correct. Then, what type of equilibrium is this? This is heterogeneous type of equilibrium because the reactants and products are present in two phases, that is solid state and the gaseous state. Okay? So, in a reaction, that reaction is maintained a equilibrium state, and in that state, if the reactants and products are present in two or more than two phases, that type of equilibrium is called heterogeneous equilibrium. Clear? Haibagi after the heterogeneous equilibrium karino hai taragadi reaction amana equilibrium state maintain tawduna laibam matamda reaction du da yariba reactant sing amasung product sing adu phase haibadi physical state ani natraga ani dagi hena present oidana yawdana lairaba adu ai taragadi adugumba equilibrium du heterogeneous equilibrium kawi. For example, oina harabda calcium carbonate solid state like calcium carbonate sina heat tawma tamda calcium oxide solid state amasung carbon dioxide gas state ani sida kaithaba ngami ado calcium oxide solid state amasung carbon dioxide gases state laiba ani sina amuk punjal laga calcium carbonate amuk hana pithorpa ngami aduna high river reaction ase reversible reaction neba ko reversible reaction orabani na equilibrium maintain tawba ngame ba aduna high river reaction jina equilibrium state laiba matamda karama makhalgi equilibrium no hai taragade mana equilibrium maintain taw lairiba equilibrium do state to heterogeneous type of equilibrium ni hagani karigeno habe matamda reactant calcium carbonate sina solid state laire aduga pithoragliba calcium oxide carbon dioxide kina kasina solid amasung gases state pithoktuno laire aduna high river reaction asida reactant amasung product singna phase ani haibadi physical state ani solid state ka gas state ka da maintain taw lairamnina masigumba ta makhalgi equilibrium sibu heterogeneous equilibrium kawi hagani. We will discuss equilibrium constant in this section, okay? Under this equilibrium constant, first we will derive the mathematical expression of equilibrium constant using law of mass action. So, to derive the mathematical expression of equilibrium constant using law of mass action, let us consider a homogeneous reversible reaction taking place in a gas or liquid phase at a constant temperature. Let us suppose that homogeneous reversible reaction is X mole of A plus Y moles of B, reversible symbol L moles of C plus M moles of D. Okay, this is the homogeneous reversible reaction, and this reaction taking place in gas or liquid phase at constant temperature. Aduna ay hojek manipuri dam hage ay koi equilibrium constant tamseba masigi chapter sida. Aduna equilibrium constant se masida tamdari se equilibrium constant gi mathematical formula expression do derivation to tamsi ka doraga law of mass action sejinarga. Aduna law of mass action sejinarga equilibrium constant gi mathematical expression derive to tamnabagi damakta ay koi homogeneous oiba reversible oiba reaction ama lokhanarasi hariba reaction si gas phase natraga liquid phase da constant temperature da thokpa reaction ni reaction ama koi khanarasi aba Hariba reaction ado madu kari reaction ne na ikhoina lograsige haiba matamda makada piriba x mole of a na y moles of b ga punjal laga ko reversible gi symbol laire l moles of c plus m mole of d pithore haiba masigi reaction se khana rasi masigi reaction se ko homogeneous hoiba homogeneous adi akhoi chang mana bhai bani liquid ta thokna liquid ta ngak to reactant su product su liquid hoiba aduga gas organa gaseous phase organa reactant su product su gaseous phase ta ngak ta thokba adugumba reversible maintain tawba constant temperature da thokpa reaction amo oina khana rase high reaction sida law of mass action apply taw taragadi ko applying law of mass action in this reaction aduna masigi reaction sida aikoi mathaki reactant dagi product sembagi aikoi gi direction masigi reaction ki direction si forward reaction kawi aduga product sing sina amok punjal laga reactant semak pagi halak pagi makhagi symbol sibuna aikoi reaction sigi direction sibuna backward reaction kawi khange ko masi aduna aikoi masigi reaction sida law of mass action apply tawseba by applying law of mass action in this reaction first let us discuss the forward reaction okay so rate of forward reaction is directly proportional to concentration of x concentration of by if we reproduce this reaction what will we get rate of forward reaction is equal to if we convert this proportionality sign into equal to we will multiply by a constant let us suppose that constant be k1 okay so instead of proportionality here I am writing equal to k1 concentration of x concentration of b let us suppose this is the equation 1 okay clear in this equation third bracket a and third bracket b represents the molar concentration of reactants a and b respectively okay x and y represents the number of molecules of reactants a and b respectively okay clear aduna aikoi masigi reaction sida law of mass action apply to yeng si haibani law of mass action apply to base ahan bada kada de apply to sige haiba matam da ko yan han bada forward reaction da han apply to si forward reaction haibadi mathaki reaction sin haire aduna rate of forward reaction mathaki forward reaction sige rate kanada depend to godagi haiba matam da directly proportional oi kanada directly proportional oi reactant singi concentration da directly proportional oi aduna concentration of a power x concentration of b power y masibuni law of mass action harise ko adidi haibagi atradi reaction amagi rese kanada directly proportional oi gaba matam da reactant to gi concentration madugi concentration da number of mole ga manaba masingna power kasinba madu da manai haibani ko aduna masigi equation se amuk reproduce to targa the rate of forward reaction se proportionality sign se equal to all a equal to all abani na masig k haiba constant amana apply to sale aduna masida si constant se k1 oina ige adu de concentration of a power s concentration of b power y hairani ko third bracket haina iri se concentration hairani ko aduna wire aduna third bracket a and third bracket b haise third bracket id masi a third bracket b sina represent to ise concentration haina haineba concentration of reactant a and concentration of reactant b harineba x ka y ga sina kaino masina reactant a ga b ga ge number of molecules to madu neba jantare ko similarly by applying law of mass action to the backward direction okay backward direction means by combining products L mole of C with M mole of D gives us X mole of A and Y moles of B okay this is the backward reaction so by applying law of mass action to the backward reaction we will get rate of backward reaction is directly proportional to concentration of C power L concentration of D power M okay because in this backward reaction C and D becomes reactant and A and B becomes product okay so if we reproduce this expression what will we get we will get rate of backward reaction is equal to K2. How it becomes? If we change this proportionality sign into equal to, we will be multiplied by a constant. Let us suppose that constant be K2. Okay. So, rate of backward reaction is equal to K2 concentration of C power L concentration of D power M. Let us suppose this equation be equation 2. Okay. In this equation, third bracket C and third bracket D represents the molar concentration of products C and D respectively. Okay. L and M represents the number of molecules of products C and D respectively. Aduna, hujik amuk. Law of mass action si mamang da tawgibagum na sab mana na backward reaction da amuk apply taw taragadi. Backward reaction haibadi L mole of C na M mole of D ga punjalaga X mole of A and Y mole of B pithorpa makagi amuk halakpa reaction do backward admadu backward reaction kawi. Hadiba backward reaction to the law of mass action apply taw saladi. Rate of backward reaction is directly proportional to concentration of C power L concentration of D power M hairani. Aduna sida concentration of C concentration of D hari karigino haiba matamda backward reaction da di C ga D ga sina reactant amuk olani aduga A ga B ga sina mabani punjalaga pithora amni na product amuk oirani dana yantai ko. Aduna masige expression je amuk reproduce taw targa de rate of backward reaction is equal to harani proportionality sign je equal to the change taw targa de constant amna multiply taw ni hare constant do ai masida K2 ne na ire mamang de K1 hai grabni na forward reaction da ko masida K2 na irasi. Aduna concentration of C power L concentration of D power M haire na si equation 2 ne thola seba. Aduna masigi expression equation je sijinariba third bracket C third bracket D hai se molar concentration of C and D hari neba. L ga M ga sina number of molecules of C and D hari neba respectively. Okay. Now at equilibrium, what will happen? At equilibrium, rate of forward reaction is equal to rate of backward reaction. Okay. So from equation 1, rate of forward reaction is equal to K1 concentration of A bar X concentration of B power Y. Okay. And from equation 2, rate of backward reaction is equal to K2 concentration of C power L concentration of D power M. Okay. So these two equations are equal at equilibrium states. By rearranging K1 by K2 by combining constant at one side, okay, what will we get? K1 by K2 is equal to concentration of C power L concentration of D power M divided by concentration of A or X concentration of B power Y. Okay. Let us represent this K1 by K2 by Kc. Then it becomes Kc is equal to concentration of C power L concentration of D power M divided by concentration of A power X concentration of B power Y. Let us suppose this equation by equation 3. In this equation, Kc is known as equilibrium constant and equilibrium constant is expressed in concentration term. Okay. So Kc is the equilibrium constant expressed in concentration term. Okay. So this equation 3 is the mathematical expression for chemical equilibrium constant in terms of molar concentration, and this equation is known as law of chemical equilibrium. Okay. So let me explain you in Manipuri also. Aduna aikoi forward reaction amasung backward reaction gi rate equation ikre reaction amagi rate speed se karino haido ikre. Aduna at equilibrium state saji kaidone forward reaction ga backward reaction gi sangsa mane haibani na equal to thamme. Forward reaction gi bahutta equation 1 dagi K1 concentration of A power X concentration of B power Y haido sinjale mane haibani na is equal to rate of backward reaction ki mahutta hojik sinjalai se equation 2 sijinaraga K2 concentration of C power L concentration of D power M haidun laire concentration term constant term gai nakal amada concentration term gai nakal amada punjan na bu honasi aduna solom da k1 by k2 haidana constant oi ba soruk tu gai nakal amada thamme adu tadi concentration term du gai nakal amada tham kan ta kai le re hai kan da concentration of C power L concentration of D power M divided by concentration of A power X concentration of B power Y hain le re k1 by k2 hariba constant 1 da constant 2 na divide tawse ko kc na represent tawrasi adu itargadi kc is equal to concentration of C power L concentration of D power M divided by concentration of A power X concentration of B power Y na lere masigi equation sibu equation 3 ne na tholase aduna equation 3 se da yauri ba kc se masi equilibrium constant kaweba equilibrium constant kram makhal gi equilibrium constant concentration term the express tawba adu gumba equilibrium constant kaweba aduna kc is known as the equilibrium constant expressed in concentration term habne molar concentration term hab aduna equation 3 pathaki se kc equal to concentration of C power L concentration of D power M divided by concentration of A power X divided concentration of B A power Y high by equation 3 se masi se boy kona chemical equilibrium constant expressed in term of molar concentration haina kawi aduga atopa maming amada law of chemical equilibrium haina su kawe yare ko aduna equilibrium constant gi mathematical expression derive to haibadi high targadi machine equilibrium constant se concentration term de express to high target su masigi equation se equation number 3 se e ge don yare ko